So in the previous video, we talked about proportions and we kind of uncovered three different things. We talked about the central limit theorem of proportions. We talked about confidence intervals of proportions. And we've also talked about hypothesis testing for proportions. So we're going to do exactly the same thing, but for means. So what I have here is kind of, let's just say we have this normal population. So this can possibly be, I don't know, the speed at which you go at when you're taking a driving test in a residential neighborhood. So let's say if you're taking a driving test and you're at a residential neighborhood, the average speed that you would usually go when you're taking a driving test is maybe 16 miles per hour. I don't know. That's what this could be modeling. So with a standard deviation of 5. So more or less, you'll be going at that rate. I don't know. This can be many different things. So let's say this is what the population looks like. So if I were to get everyone's speed that historically of people who took the driving test, this is kind of what it's gonna look like. Okay. So what I'm gonna be doing is that I'm going to take a certain samples from this population and calculate a mean. So basically, this is what I'm doing. So I'm gonna take sample sizes of size 5. So I'm gonna take 5 speeds. Okay. And so let's say I grabbed 5 different people, I recorded their speeds, and I added them together, and I got a mean, okay? So maybe this guy was maybe like, I don't know, 14 miles per hour. This guy was maybe 15 miles per hour. This one was 16 miles per hour. And these guys were kind of speeding, so maybe 20 and 21 miles per hour. So what I'm going to do is I'm going to add all these numbers up and add them together and divide it by a total and get a mean. And then what I'm going to do, I'm going to get another random 5. And I'm going to calculate another mean. I'm going to do the same thing. Get another 5. And I'm going to calculate another mean. So I'm going to keep doing this continuously until I start getting some sort of shape for my mean. So if I do this 10,000 times, then you can see that the means of these entire different observations of the parent population looked really normal. Okay, so this is really, really cool because that means if I were to get different means from the original population, I will just get a normal curve. Okay, and if we look at the stats, the mean of the original was 16. The mean of the sample mean was 16. Okay, the only thing that really changed was the standard deviation. So basically what that meant was that this original curve got a lot more skinnier. Okay, so now let's go ahead and see what happens if I increase the number of samples to maybe 25. So if I animate it, now I'm going to increase n. So now instead of getting 5, I'm going to get 25 random samples from the parent distribution. I'm going to add them all together and divide it by 25. And then what I'm going to get is one mean. So I added all of these guys up, all of the random ones, and I got a mean. I'm going to do this many, many different times, maybe 10,000 times, and you still get a normal curve. The only thing that's different is that now the standard deviation got much smaller. You can see that the mean stays the same. It's always centered in the middle, but the standard deviation got skinnier. And actually this should make sense because you're getting closer and closer to the true value if you kind of think about it that way. Okay. So now let's say we don't have a normal curve. Let's say we actually have something that looks like that. So do you think that if I were to get maybe 5 samples, again, I got 5 random samples from this uniform distribution, add them all together and divide it by 5, would I still get a normal curve? Well, we can keep doing this over and over and over again. All right, calculate a mean. Let's see what happens if I do it 10,000 times. I still get a normal curve. Notice that the mean have been the same and the standard deviation get a little smaller also. So even with the normal curve, it starts showing this kind of normal curve. If I were to get 25 and do this 10,000 times, you can see now that again, this curve got smaller. Okay, so there's less variability. Okay, so let's say, for example, we have a skewed distribution and we're only getting 5 samples. So I animate it. So basically, I'm going to get more samples from over here because this is where it's more likely to occur. So I'm going to keep doing that over and over and over again. Add them together and get a mean. I'm going to do it many different times. But now you kind of see that, you know, it's not quite normal. You can kind of see a little bit of skewness, okay? Just a slight. But what happens if I increase to 25? If I increase my sample size? And I do this many different times. Let me just do 10,000. You can see now that you kind of get this nice normal curve. So even though it was skewed, when n equals 5, we didn't quite get an exact normal curve. But when I increase the value of n, it started becoming better. Now, I can just make this curve look however the heck I want. So I can make it look like that, okay? And customize it, okay? So will this also give me a normal curve? Well, if I keep doing this, I get 25 samples. Okay, I'm not going to bore you with all that. But I'm going to get 25 samples, add them all together, divide it by 25, and you're going to get a new mean. If I do this many different times, oh, that's not animated. You start seeing a normal curve. Now, this one also isn't as nicely normal. So maybe at 25, that might still be a little too small. Okay, so basically what we're saying is that the initial population, it doesn't really matter what it looks like. If I were to get random samples from this unknown distribution, from this parent population, and I get many different samples, my graph is going to start looking like a normal curve at a certain point, okay? Maybe it's not n equals 25, okay? So let me kind of explain a little bit in words of what exactly is going on here. So this, make sure that you write down. So this is what we call the central limit theorem for sample means. So suppose that x comes from a population that's not necessarily normal, okay, with a population mean of mu and a standard deviation of sigma, okay? So we have a mean and a standard deviation that we know from this parent population. So the sample mean, x bar, is approximately normal with a mean of mu and a standard error of sigma over square root of n for sufficiently large n. So x bar is normally distributed with a mean mu and a standard deviation of sigma over square root of n. Okay, so that's what that means. So it's very similar to the population proportion, but remember the population proportion was that p hat was normally distributed with p and then square root of p1 minus p over n. Okay, so the central limit theorem says this. Now the key word here is, what does it mean by large n? So what exactly does this mean? Because with proportions, what we had was that the np has to be greater than or equal to 10, and n1 minus p had to also be greater than or equal to 10. For means, what we have is that n, so what does it mean to be sufficiently large? In this class, we're going to say that n has to be greater than or equal to 30. That's what we're going to say. That's what's going to satisfy this this central limit theorem. So basically, our sweet spot is going to be n has to be greater than or equal to 30 in order to be able to do this type of problem. Okay, now notice that when it was normal, it was okay. Okay, because if it was normal, then you got a normal curve. So if you go back and I switch this to normal, notice that it didn't matter what n was. I can say n equals 2 and do many different things. I still get a normal curve. So with normal, it didn't matter how many sample size that we got. I still got a normal curve. It's only when you start looking at skewed and weird distributions where this doesn't quite look normal anymore. You got to be able to increase the sample size to be able to get this normal curve, okay? And our sweet spot is going to be n equals 30. So basically, when the population distribution is normal, the sample size does not matter. So it doesn't matter what the sample size is, you will always get a normal curve. Always get a normal curve for x bar. You're always going to get a normal curve. So it doesn't matter. If we know that initially it's normal, n doesn't matter. It can be 2, it can be 3, it can be 1, it doesn't matter. It's still going to be normal. When the population distribution is not normal, so if we have like uniform or or I don't know, skewed, x bar will be normal as long as n is greater than or equal to 30. Okay? And the third one, if not normal and n is less than 30, x bar is not normal. Okay? Okay, so that's basically, this is going to be really important because we'll do a couple problems in the next video on how to identify when we can use a central limit theorem or not. Okay, so the sweet spot here is that n has to be greater than 30 in order for me to get a normal curve. Okay, so one thing to note, just to explain really quickly of where these numbers came from, notice that when we, regardless of whatever the population distribution looked like, the mean always was the same. Notice that here the mean of the skewed distribution was 8.08. The mean over here was 8.07. So they always are around the same. That's why the mean of the original, if it's mu for the original, is going to be mu for the sample mean. Okay. Now for the standard deviation, if it's sigma, it's not going to be sigma. Okay, you can see here that sigma, the standard deviation here was 6.22. Here it decreased to 1.26. And the factor that it kind of decreases by is 1 over square root of n, which is this one. Now, to kind of prove this is a little bit complicated. We kind of have to find the variance. But don't worry about it. All you have to do is use this particular, you have to know how to use this formula. So in the next video, we'll do some concrete examples. So maybe this was a little bit intuitive. Maybe you got it, maybe you didn't. It's okay if you didn't get it. I want you to be able to understand how to do problems of the central limit theorem for means and how to identify them.